looks pretty approximate, but there's no like geo stuff. Yeah, that's yeah. It says read plus y.
All right, welcome everyone. So when we left off last time, we were working on this set of problems on applying the central limit theorem. And we had talked about problem 3, computing a sample size to get a probability of at least 0.9 of being within a certain range of the true mean. So I think based on that, you'll be able to solve problem 4 on your own. So I will leave you to do that on your own if you would like, and I'll post a key for that on Canvas. But I did want to talk about problem 5, which is a little bit different. So take a moment to read that and think to yourself about what strategy you might use. All right, so our key idea here is we want to find the probability that the total service time is less than 1 hour. Well, that's just the same as saying we want to find the probability that the average service time for these 60 customers is less than 1 hour divided by 60, or less than 1 minute. So now we've rewritten this in terms of a probability involving y bar. So now this is a similar sort of question to what we solved in problems 1 and 2. Give this a try from here. All right, so according to the central limit theorem, y bar, or we could write this as y bar sub 60 to specify the sample size, is going to be approximately normal because 60 is a relatively large sample size, with a mean of 1.5, so the same mean as the individual service times, and a standard deviation of the standard deviation for the individual customers, which is the square root of the variance, divided by the square root of the sample size. So we can then switch over to R, share my screen again. And use P norm to find the probability of something under the normal distribution curve. And we can find the probability of being less than 1, because that's what we're interested in finding the probability of, with a mean of 1.5 and a standard deviation of square root of 1 is 1, divided by the square root of 60. So 5.38 times 10 to the negative 5th. Questions about this? All right. So let's talk about our new topic, which is the normal approximation to the binomial distribution. So to get us warmed up, let's recall from Math 346. Let's let y be the number of heads that you get on n independent coin flips that each have the same probability of heads p. What distribution does y have? Okay. Yeah, that's binomial because we have a fixed number of trials, n, and they each have the same probability of success p, and they're all independent. And then the thing we want to count is the number of successes. Specifically, it's binomial with parameters n and p. So what is the mean of y going to be? N times p is the expected value of y, and the variance of y is n times p times 1 minus p. All right, so now, oops, right, and then the standard deviation of y then is the square root of the variance, just to make that explicit. All right, so now let's think about these same coin flips a little bit differently. So now let's define a random variable x sub I that equals 1 if the ith coin is heads and equals 0 if it's tails. So how does y, that we defined on the last slide, how does y relate to the x sub i's? So y is the total number of heads that you get on all n coin flips. Davis?
The sum of the x of x.
Yeah, y is the sum of the x sub i's as I goes from 1 to n. So that means we could divide both sides of that equation by n, and we get y over n is equal to 1 over n times the sum of the x sub i's, which is otherwise known as x bar, the mean of the x's. All right, so if n is large, what's the distribution of x bar? Thinking about what we did on Monday. Kyle. Like the name of the distribution. Isaac?
More normal.
Yeah, if n is large, then the distribution of x bar is going to be approximately normal. Because we just talked about the central limit theorem telling us that no matter what the distribution of the x's is, as n gets large, the mean of the x's approaches a normal distribution. So that tells us that y over n, which is x bar, that thing is approximately normal. And then based on that, what can we say about y is our question. Well, back in Math 346, we had theorem 6.3 that told us that if z is our normal random variable, then if a and b are constants, a times z plus b is also normal. And we proved that with moment generating functions. Remember that that's not true for all distributions. It works specifically for the normal distribution. That if you start with a normal distribution and multiply and add constants, you stay with the normal distribution. All right. Well, y is just n times x bar, or n times this y over n. So that means that if y over n is approximately normal, then theorem 6.3 tells us that y is also approximately normal. With mean mu equal to n times p, and sigma equal to the square root of n times p times 1 minus p. So same mean and standard deviation as we saw back when we were thinking of y as a binomial random variable. And now we're saying that y is also approximately normal. Questions so far? All right. So our takeaway here is that for large values of n, we can use the normal distribution as an approximation to the binomial distribution. So for example, suppose you survey 100 UWEC students to find out if they're vaccinated against COVID. If the true proportion of people among all UWEC students, so the whole population, if that true proportion who are vaccinated is 0.68, that is the latest value that I've seen for the proportion of people who have uploaded their vaccination information to the university. What's the probability that between 65 and 70 people in your survey say they're in favor? And we'll do this calculation inclusive, meaning including 65 and including 70. So we can solve this problem in two ways. One way would be to compute the exact answer. That's using a binomial distribution. Give that a try. So here we want the probability that y is greater than or equal to 65 and less than or equal to 70. So we're going to compute that by finding the probability that y is less than or equal to 70. And then you subtract the probability that y is less than or equal to 64. So remember that this lower bound here changes because we want to include the probability that y could be exactly equal to 65. We want to get rid of the probability that y is less than or equal to 64. So here's what that looks like in R using P binom of 70 with a sample size of 100 and P equal to 0.68. minus p binomial of 64 with the same n and p. So we get 0.47577. Questions about that? All right. So the other way we could do this would be an approximate answer using the normal distribution. So to do this, we're going to say we want the probability that y is between 65 and 70. But because the normal distribution is continuous, it actually gives a probability of 0 of y being exactly 65 or exactly 70. So because of that, we tend to get more accurate results if we instead say that this is approximately the probability that y is between 64.5 and 70.5. Oops. So this is called the continuity correction, where we expand the interval we're interested in by 0.5 on either side if it's an interval that's bounded on both sides. Davis.
Is there a reason to use 0.5 so it's closer, like 70 points? Just out of curiosity.
The reason is that if you're going to pick a single number that's going to give you the best results, sort of overall possible values of n and p, 0.5 tends to be a good central value. I have not seen a proof of why 0.5 is the one that tends to work best. That's a good question. Isaac.
And we always round that 0.5 like up or down on the bounds, like out.
Right, you always do it in whichever way makes the interval bigger. And then we want to compute the mean and standard deviation that we expect for that normal distribution. So the mean is going to be n times p, so 100 times 0.68, so 68. And the standard deviation is the square root of n times p times 1 minus p. So that ends up being the square root of 21.76 in this case. So go ahead and try using a normal distribution to compute the probability that y is between 64.5 and 70.5. So our exact answer for the binomial was 0.476. Here we got 0.477. So pretty close. Questions about this process? Kyle.
Why don't we divide it by the square root of n SD? The square root of 100.
Good question, because when we compute the standard deviation this way, we're using the formula for the standard deviation from a binomial. So the binomial distribution is going to have exactly this standard deviation. So we just go ahead and use that as our standard deviation. The other way to do it would be to say the standard deviation of the individual x sub i's. Sorry, I should stop sharing my screen so Vivian can see this. Would be, this is a binomial random variable with an n of 1. So this standard deviation would be square root of 1 times p times 1 minus p. So then when you calculate the standard deviation of y, let's do the variance of y first. That's going to be the variance of n times x bar. So n squared times the variance of x bar. So n squared times the variance of x bar is the variance of one of the x sub i's divided by n. So n times the variance of x I is n times, oops, not the square root, we're no longer dealing with the standard deviation. 1 times p times 1 minus p, which gives us the same thing. So the standard deviation of y then is the square root of n times p times 1 minus p. So this is the standard deviation of y calculated using the, take the variance of x sub I and divide it by n. But it has this extra thing of the fact that y is not x bar, y is n times x bar. So that ends up getting multiplied in. So we cancel out one of the ends. So you get the same standard deviation of y, regardless of whether you are looking at it from y as a binomial random variable, or looking at it as what would we get if we use the central limit theorem. But you just have to sort of go through more steps this way. Kyle, does that answer your question? Okay. Other questions about this one? Share my screen again. Okay, so in practice, nowadays, usually we have access to computers or calculators that can do the binomial distribution and the normal distribution equally easily. So in practice, we often don't end up needing this approximation. The time when it's useful is if all you have is a normal probability table and maybe a 4-function calculator. So this ends up being very useful on actuarial exam P to be able to solve problems about the binomial distribution, even though you don't have a calculator handy that can do those computations for you. The other reason why we're covering it is because some of the methods that we're gonna talk about in chapter 10 are working with binomial random variables, but the way the methods work is based on the normal distribution. So this normal approximation to the binomial is helpful for being the underlying reason behind why some of those methods are gonna work. All right, so one important question is how large should n be in order to use this approximation? Does anybody have any guesses based on what we talked about on Monday? Kyle? Bigger than 30? Yeah, that's a good guess. And if we say simulate binomial random variables with n of 30 and p equal to 0.5, yeah, that looks pretty good. Here's what it looks like when n is 30 and p equals 0.1. So there a normal distribution doesn't look so good. So in the case of the normal approximation to the binomial, we don't just want to use our blanket n is greater than 30 guideline. We instead want to base our decision based on both the value of n and the value of p. So a good guideline is that the normal approximation is going to be a good approximation if our sample size n is greater than 9 times the ratio of p and 1 minus p, p and q, where you put whichever one of those is larger in the numerator of that ratio and whichever one is smaller in the denominator. So for example, take a look at problem 1 and decide whether the normal distribution is going to be a good approximation. So Vivian, this is the normal approximation to the binomial. Which is right here. All right, so we'll see thumbs up for yes, the normal distribution is a good approximation. Thumbs down for no, it's not so good. Yeah, thumbs down. Niall, why is it thumbs down?
Because 9 times 0.95 divided by 0.05 is 171.
Yeah, so here P is 0.05 and Q is 1 minus that, so 0.95. So we have 9 times the larger of P and Q, so 0.95, over the smaller of P and Q, 0.05. And that ends up being 171, you said?
Yep.
So our value of n was 160. Is less than that. So the normal distribution is not a good approximation. So that means you can go ahead and compute this probability using a binomial distribution. Give that a try if you haven't already. Good question. So there is another way of testing whether the approximation is accurate based on the standard deviation. It's like standard deviation is away from the mean, and that ends up getting squared and turned into a knot. what happens if I exactly. So it looks like you found the probability, 5 or fewer probabilities not show up. No, because he found probability that 5 or fewer would not show up. So then 1 minus that is probability that 6 or more would not show up. So you are not counting for exactly 150. Yeah. So you found the probability that this is probably that 5 or fewer do not show up. So 1 minus that is the probability that 6 or more do not show up. So you are not accounting for the possibility that exactly 5 do not show up. So go ahead and work at your own pace. I'll throw up some of the answers to some of the following questions on the board so you can check your work. right, are there any questions about these problems that you've been working on? The main thing I saw was a couple people were solving problem 1 in terms of the number of people who didn't show up instead of the number of people who did show up. If you're doing that, then you want to find the probability that, say, x is greater than or equal to 5, which is 1 minus the probability that x is less than or equal to 4. So if you started by using binomial CDF of 5 and then took 1 minus that, then your answer was slightly off because you didn't account for exactly 5 people not showing up. All right, nice job today. I will see you in lab tomorrow for doing the normal approximation to the binomial in R.